When you're dealing with applications of maximisation and minimisation, you'll generally be given worded questions where you've got some kind of problem to solve and you need to find the maximum or minimum value that will give you some solution. So you need to generally write your own equation using your own pronumerals. Now we're used to seeing our equations in the form y equals something with some x's of some form over here. So remember that the x, or whatever is on the right hand side, is going to be your variable. That's the thing that can vary, or the thing that you don't know. And let y, or whatever pronumeral you choose for the left hand side, be the thing that you're trying to maximise, because that way you can differentiate y with respect to x, or whatever pronumerals you've used, to find how to make y as big or as small as possible. Now, if you can draw a picture, that's useful, and recall the relevant formulae. So you might be asked about the volume of a cylinder, in which case you need to be thinking volume of a cylinder is pi r squared h, or you might be asked something about interest or whatever, so you often need to draw on previous knowledge. You need to know any restrictions that are on the domain. So it could be that you're dealing with the radius of something, trying to maximise surface area. Well, you need to remember that radius can't be negative, it's going to be a positive number. Similarly, time might not be able to be negative. So always look at the context and think about how big or small your variable could be. Then it's just a matter of actually finding the global maximum or the global minimum. Now, as you know, the way to do that is to check the stationary points, because that's where you find the high points and the low points. And you do that by differentiating and letting the first derivative equal 0. You'll also need to find the nature of the turning points, and the easiest way to do that usually is to differentiate again and see if the second derivative is positive, in which case you'll have a minimum, or negative, in which case you'll have a maximum. You should also check the boundaries of the domain and any discontinuities that might be in your function. And if you can, sketch it. It might be that you're solving something as simple as y equals x squared minus 3, and if you know that that's a parabola that looks like this and goes through minus 3, and they say what's the minimum value of this, you don't really even need to differentiate or find stationary points. This is one that you can solve with a simple sketch and a little bit of logical thinking. Now what's important is that if you've been given a worded question that says, what's the maximum surface area if something or other, or what's the cost if I have this much interest, or something like that, you can come up with x's and y's to solve the problem, but if they weren't actually in the question, then you shouldn't use those variables or pronumerals in your answer. Instead, write a careful conclusion that actually answers the question in basic terms. So don't say x equals this if there was no x in the question. Say the distance needed to maximise the something is whatever. So it's really clear that you've answered it. So here we have an example. An open rectangular box is made by cutting square corners out of a square piece of cardboard that's 60 centimetres by 60 centimetres and folding up the sides. What's the maximum volume of the box and what are its dimensions then? Okay, first thing to draw here is a picture showing what we're dealing with. Now we've got a piece of cardboard that's 60 centimetres by 60 centimetres. So drawing that up first is the best way to start. Now we're cutting some square corners out, but we don't know how big those square corners are. So on your drawing, just make them all the same size and think to yourself, now what is the variable here, the thing that we don't know? Well, the thing we don't know is how big those corners are. So if we just pick a variable, you can pick anything you want. I'm just going to call mine x and say if we let these lengths here be x and x, now I've got something to work with. So that's all of those distances are x's. All right, if we know that this is 60 centimetres then, how big is this part here if we've taken off x and another x? Well, it'll be 60 minus 2x, won't it? So drawing your diagram and then just thinking through what you need to do to make your box is how you should start. I can picture that this will be the base of the box, and these bits here, once I've cut the corners off, will make my sides. So that means I've got 60 minus 2x and 60 minus 2x. This will be a square base on my box. And the box will be x tall, won't it? So now I can come up with an equation for the volume of my box. I know that volume equals base, the area of the base times the height. And the area of the base is going to be 60 minus 2x. squared. And then I'm going to need to multiply that by the height, which is going to be x. So I'll pop that in front. Now, we could leave this volume formula like this and differentiate it and play around with it as it is, or we could expand it out, and then when you differentiate, you can differentiate one term at a time. It's up to you. You'll need to use the product rule if you differentiate it in its current form. It doesn't matter which way you go, whichever way you just start, that's absolutely fine. I'm going to start by expanding it out. So I'm going to get 3,600 minus 240x plus 4x squared. And now I need to expand this. I'm going to start with my x cubed term, so 4x squared times x is 4x cubed, and x times this gives me minus 240x squared, and I've got plus 3,600x. So that's my volume formula based on my variable x. Now I'm trying to find the maximum volume of the box. So if I could graph the volume based on x, all I need to see is where are the high points. Now it looks like a cubic curve, doesn't it? And we know cubic curves that are positive either go up like this, or with something at a flat spot, or with a big wobble. Now we need to also think through what are the limitations on x here, because can x be as big or small as it wants? Well, look at your picture and just imagine you've only got 60 centimetres of cardboard. So if you make x 0, you've got nothing to fold up. It's not going to have any volume at all. And you're trying to make your box as big as possible. So clearly x has to be bigger than 0. But x can't be too big. If it was any bigger than 30 centimetres, then you'd have no base left on your box. The whole thing would be corner. So it's worth thinking through here that x has to be smaller than 30 and greater than 0. So on the edges of its domain, wherever it's going to sit, we only want to look in this area for the highest point. Now, we should have a check for a maximum turning point, because that's going to give away a high point nice and easily. We know that the edges of the domain, in this case, aren't going to give us the maximum volume of the box, because we'll either end up with nothing to fold up, or no base and all side. So we're looking for this point here. All right, how do we do it? Well, we need to differentiate the volume to find when it has its maximum. So differentiating one term at a time here is quite straightforward. We get this. Now we need to let the first derivative equal 0 to find the flat spots in our volume curve. So if we let this equal 0, I can actually factorise this by bringing a 12 out the front. That gives me x squared minus 40x plus, what have we got, 300. Now I can see I've got a quadratic in here, so I can factorise it even further. Now, if I divide both sides by 12, that 12 is just going to go, isn't it? So that keeps things nice and straightforward. And I can say that 0 has to be equal to, now I need to think of two numbers that multiply to make 30 and add to make minus 40. I'm thinking minus 10 and minus 30 will do it. So that means that x equals 10 or 30. Now think back to your restrictions. You know that x can't be 30. If it is, we won't have a box. So we actually want to investigate this one when x is 10. So this will give us our maximum turning point. Now you should check that this really is a maximum turning point when x equals 10. Check that it's not actually a minimum. How do we do that? Well, we have two methods. You could look at the gradient when x is 9, say, and 11, and just check that it's going up and then across and then down. But that involves quite a bit of subbing in. I think it's probably quicker and easier just to find the second derivative and see what that would be when x is 10. So the second derivative, if I differentiate this one, gives me 24x minus 480. So finding some more board to work on here. When x equals 10, the second derivative is going to be 240 minus 480. It's going to be negative, isn't it? And that means it's concave down. So therefore, we've got a maximum turning point when x equals 10. And that's what we were looking for. So that must be when our volume is maximal. So look back and check what the question asks. What is the maximum volume of the box? And what are the dimensions then? Well, let's say maximum volume Now, how do we find it out? Well, we've got a formula for the volume in terms of x, and we know what's going to happen when x is 10. So sub 10 in. 60 minus 20, that's 40. 40 squared, that's 1600. Times 10, 16,000. And we're in cubic centimetres. And what are the dimensions then? Well, refer back to your picture. The base will be 60 minus 2x. So if x is 10, it'll be 60 minus 20, so that's 40. So we'll write, and dimensions are 40 centimetres by 40 centimetres, because it's the same there and there, and the height would be x, which is 10. And then just double check that you've answered both parts of the question, and we have, so we're finished.